Welcome to Chemistry with Caroline. In this video, we're going to learn how to identify electron donating groups on aromatic rings. So we'll look at how to identify them, how they push electron density into the ring, and where that electron density lies. So generically speaking, you have some substituent on a ring, X, and we're going to look at what the specific X's will be shortly, and that is pushing electron density into the ring so that the ring is more electron rich. And it can push electron density into the ring either via resonance, which is a larger impact because you're pushing electrons around that pi system, or via induction, which is going to be the sigma framework, so just the unequal sharing of electrons in a sigma type bond. So resonance refers to our pi system, and induction refers to our sigma system. This benzene derivative is called aniline. It has an NH2 group on there, and that NH2 group is an electron donating group. Students often have a hard time identifying electron donating groups, but there's actually a pretty easy trick, and that is that this nitrogen has a full octet, and it's a second row element, so it can't exceed that octet, which means I can't bring any electrons out of the ring like that, because I would then have more than 8 electrons around that nitrogen. It has 3 bonds and a lone pair on it. So this doesn't work, okay? So if you can't bring electrons out, what you can do is push them in, and that makes it an electron donating group. So let's redraw this structure here. Now, speaking of breaking that octet rule, if I bring these electrons down and push them towards the ring, I also have to move this pi bond out as a lone pair of electrons onto that carbon, so I don't break the octet rule for the carbon that the nitrogen is attached to. So that will give me a resonance structure that looks like this. So the overall charge on my structure is 0 still, right? I have a negative carbon and a positive nitrogen, just like it was at the beginning, but I do have 2 charged atoms. So now these electrons can fold in, and these can go out onto that carbon atom. So once you're in the ring, you can move around the ring with that charge. And then these electrons can come out, and those will go onto the carbon. So see how my arrow for the first arrow there ends in the middle of the bond? That tells me that I'm going to make a double bond there. And then the second arrow ends at the carbon atom. That tells me that I'm going to make a lone pair of electrons there. And then these can pop back out, and those can go back onto the nitrogen. So we're drawing resonance structures to show where the electron density lies in the molecule. It's sort of a limitation of a Lewis structure that suggests that electron density is shared evenly, but electrons are not static. They can move around the ring. So if we think about this overall structure, you're going to have a partial negative charge at the positions next door to the substituent and the position across from the substituent. And that ring as a whole has more electron density in it. It's an electron-rich ring because the substituent attached to it is pushing electron density into the ring. And in this case, for this derivative, resonance is the way that those electrons are being pushed into the ring. You can also have a substituent that pushes electron density into the ring via induction, which is just basically the sigma framework, so those single bonds in the molecule, how the electrons are being shared. An sp3 hybridized carbon is less electronegative than an sp2 hybridized carbon, so electron density is going to be pushed more towards the ring, and that is going to make the ring a little bit more electron rich. So essentially, the electrons are not shared completely evenly because of the different hybridizations of the substituent carbon, the CH3, which is sp3 hybridized, right? And then all of the carbons that are inside the ring would be sp2 hybridized. And so this is an inductive effect. It's just the unequal sharing of electrons due to differences in electronegativity and therefore affinity for electrons. So there's sort of three main electron donating groups that you'll see, and the most electron donating group is Nr2, so it's going to be attached to the ring. And in these cases, R is going to either be equal to an H or a carbon atom. So you could have a lot of different derivatives, but the R group will have to be some iteration of H or C. Then you would have an oxygen that's directly attached to the ring. And then lastly, you would have a carbon that's sp3 hybridized that's directly attached to the ring. So that wouldn't have any lone pairs. So the top two here, the nitrogen and the oxygen, this would be via resonance. They can actually push electrons around that pi system with their lone pairs of electrons. The Cr3 would be via induction. So the Nr2 group is the most electron donating group, and the Cr3 group is the least. The Nr2 group, as we saw, it becomes positively charged when it participates in resonance. Nitrogen is less electronegative than oxygen, so it would be less destabilized by that positive charge, and so that makes it a more electron donating group within that framework. So you really only have to know these three derivatives. Any of them would be an electron donating group, and the nice thing is then you won't be phased by what R is, right? R could be a methyl or an ethyl, it could be an isopropyl, it could be H's, but you know fundamentally that the direct attachment of nitrogen to the ring when it has H's or C's on it makes it an electron donating group. So the electronic character of the ring can impact things like reactivity. We're going to revisit this type of phenomenon when we think about electrophilic aromatic substitution reactions and where a new group goes. It can impact the spectroscopy that we observe with a system. So what is the chemical shift of those compounds going to be? So understanding a basic principle like this has wide-ranging implications across organic chemistry. So that's been a look at electron donating groups. If you found this video helpful, please like, subscribe, and share with your friends, and I'll see you next time.